And here's our third example of how to use Newton's second law. As you can see, these problems are going to get a little bit more complicated as we go along, as the examples continue. Here you can see we have a wedge-shaped object with a mass on top of the incline, and then we have another mass hanging from a string attached to the first mass over a pulley. And you can see that from intuition, if this is a 10 kilogram mass and this is an 8 kilogram mass, that this big mass will probably pull the smaller mass up the incline. There's going to be an acceleration in this direction. So the assumption is that the acceleration will be like this. The question is, what is that acceleration, and what is the tension in the string over here, and what is the tension in the string over there? All right, now we can solve this in various ways. We can use what we call free body diagrams on each component here. So we can take a look at the free body diagram here, we can take a look at the free body diagram here, and then we can solve them simultaneously, and we can get the answer that way. Although I like to reserve that kind of methodology to more complicated problems where that's really the only way we can do it. There's actually an easier way in which we can solve the problem. We can look at the 8 kilogram mass, the 10 kilogram mass, and the string in between as a single system, and we can look at all the forces acting on that system. So if we use that technique, we'll go ahead and look at all the forces that act on the system, and so we do not at this moment need to worry about the tension on the string because that's part of the system, and so we can ignore that for now. So we're just simply going to find out what are all the forces acting on this whole system. Also notice that, I didn't write it down, but I'll just say it, that the friction between the incline and the mass here is equal to 0. So we'll look at this as a whole system. What are all the forces acting on it? So first of all, we have the force of gravity pulling down here. So this is m1g. And since this is on an incline, we're going to draw the perpendicular component and the parallel component to the incline. So this would be m1g times the cosine of theta, and this is m1g times the sine of theta. All right. Now, of course, we still have the reactionary force of the force pushing down perpendicular and incline. So we'll have the normal force pushing back this way. That's the normal force, and that's equal in magnitude, opposite direction to m1g cosine of theta. So they will cancel each other out. Notice I can now ignore this because I've divided this into the two components right there. Then we still have another force acting on the system over here. We have the weight of this mass pulling down. This is m2g. And notice there's no reactionary force because it's not resting on anything, so there's nothing pushing back. Now, what are the two, well, I kind of gave it away, didn't it? What are the two forces that are now acting on the system? The two net forces, or the two forces that make up the net force on the system? It would be this force right here, and it would be this force right here. Now, you say, well, how can you work with that? Because this force is pushing this way or pulling this way, this force is pushing this way, and they're not pushing in the same direction. Well, in a way they are, because here you have a pulley, and the string that connects the 8 kilogram mass and 10 kilogram mass goes around this pulley. It just kind of redirects the tension or the force around that pulley. So in a way, this force right here is taking the whole system and pulling it like this. This force is taking the whole system and pulling it like this. And if this is bigger than this, the system will accelerate in this direction. If this is bigger than this, then the system will accelerate in this direction. So it's okay to think of this as being two opposing forces, even though they're not pointing in a linear direction. All right. If we then take that as the assumption, we can say that F net is equal to mass total of the whole system times the acceleration of the system, or the acceleration is equal to F net divided by the mass total. Now, I'm going to take the assumed direction as the positive direction. In other words, this acceleration from there up and this way is going to be considered the positive direction for the acceleration. So any force pulling or pushing in that direction, I'm going to call a positive force. Any force opposing that in the opposite direction, I'm going to call a negative force. So we have this force right here, which will aid the acceleration. So this would be equal to m2g, and I'll call that positive, minus this force right here because it opposes the acceleration. So it would be equal to m1g sine of theta, and the whole thing divided by the sum of the two masses, m1 plus m2. And that's how I can find the acceleration of the whole system. All right, plugging in the numbers. So this is equal to m2, which is 10 kilograms, times 9.8 meters per second squared, minus m1, which is 8 kilograms, times 9.8 meters per second squared. Let me move out of the way so you can see that. I still have to multiply times the sine of theta, and that would be the sine of 30 degrees. And the whole thing divided by the total mass, which will be m1, which is 8 kilograms, I believe. Yeah, m1, 8 kilograms plus 10 kilograms. Okay, simplifying that a little bit, that would be 98 newtons, minus, that would be half of this would be 4 times that, that would be 39.2 newtons, all divided by 18 kilograms. At this point, I'm going to need my calculator. Never leave home without it. 98 minus 39.2 divided by 18, and I get 3.27, so that's equal to 3.27 meters per second squared. All right, so now I have my acceleration of the system, which means this will accelerate in this direction at 3.27 meters per second squared, and this will accelerate up the incline at 3.27 meters per second squared. Now, I need to find, so I got the acceleration, now I need to find the tensions. I'm going to now concentrate on this right here. So, take the mass, m2 at 10 kilograms, so this was equal to m2, and I have the force of gravity pulling down on it. I like to use blue for that. So I have the force this way, so it would be m2g, and then I have a force pulling upward, and that would be tension 2. Now, which of those two is bigger? Well, it appears to me that m2g should be bigger than t2 because the acceleration in this direction, so that makes sense. What I could do here is I could use the second law of thermodynamics, but the second law of Newton, that we can say that F net equals m times acceleration, and since the net force would be m2g minus tension 2, because again, I'm assuming the acceleration to be in this direction, so I'll call this the positive acceleration, so it's this minus this is aiding, this is opposing the acceleration, and that is equal to m2 times a. And so therefore, if I solve this for t2, I can say that if I move this over there and move this over here, I get m2g minus m2a equals t2. And reversing the equation, t2 is equal to m2g minus m2a. All right. Now if I plug in the numbers, m2 is 10 kilograms, so that's 10 kilograms times 9.8 meters per second squared, minus 10 kilograms times the acceleration of 3.27 meters per second squared. And what will that give us? So I have 9.8 minus 3.27 times 10, or 65.3 newtons. So that would be T2. Now, what about T1? Well, it turns out that T1 should be equal to T2. Now, why can I say that? Because it's a single string connected from one mass to the other mass, and so whatever the tension is here must be the tension there, assuming that there's no friction on this pulley and the pulley has no mass. So in other words, the mass is so small we can ignore it, and so we don't have to worry about the moment of inertia. That's something for a different topic. So we can say, therefore, that T1 must equal T2. And therefore, that is equal to 65.3 newtons. Now, what if you say, well, I don't necessarily believe that. Show me, prove to me that that's the case. Another way in which we can look at it is that T1 is the force required to hold up this mass against the m1g sine theta component, plus the acceleration of this mass of the incline at this acceleration. So another way of looking at it is say, well, I can say that T1 must equal to m1g sine theta plus the m1a. So it's the force required to hold up this mass against the gravity component along the incline, plus the force required to pull this mass up the incline. And if we plug in the numbers there, we'll get the same answer. Well, we can see that's true. And 1 is 8. I'll leave out the units, 9.8 sine of 30 degrees is 1/2, plus the mass, which is 8, times acceleration of 3.27. And if you now plug that into your calculator, so you have 8 times 9.8 times 0.5 plus 8 times 3.27 equals, sure enough, times 10, 65.4, so that gives me 65.4 newtons, which of course is the same, almost the same, slight round-off error, because I didn't take it off to enough significant figures, but as you can see, you get the same answer. Now, one more thing. Coming back over here and looking at this situation right here, an easy way to figure out what the tension in a string is that has something suspended from it, which may or may not be accelerating, is that the tension, in this case T2, is always going to be equal to the weight of this object, which is, in this case, m2g, plus or minus the force required to accelerate it, m2a. Now, I said plus or minus. Well, it is plus if the object is being accelerated upward, because then not only do you have to hold it up against gravity, mg, you also have to have additional force accelerated upwards against gravity, so in that case it would be m2g plus m2a. But if the object is allowed to accelerate downward, then you don't need as much tension in the string. You need enough to hold it up against gravity minus the force that will allow us to accelerate downward with gravity. So in that case, it will be m2g minus m2a. Remember the equation that we ended up with when we used Newton's second law on this free body diagram? Indeed, we did get m2g minus m2a. So it'll always be mg, well, in this case it was m2, of course, but it'll always be mg plus ma or mg minus ma, plus if it's accelerated upward, minus when it's accelerated downward. And of course, if you look at it over here, it'll be mg, of course, times the sine of theta because it was an incline, plus ma because it was being accelerated up the incline, so I had to add the plus ma to it. And that's how you do problems like that.